Here is a question. If you are given a matrix, how do you know upfront whether it can be inverted at all before you go through the trouble of actually calculating the inverse? I am Pradeep, and the answer is a single number called the determinant. The determinant is a number you calculate from a matrix, and it tells you one thing: can this matrix be inverted or not? If the determinant is 0, the matrix has no inverse. If it's anything else, it does. So, how do we calculate this? If we consider a matrix with A, comma B in the first row, C, comma D in the second row, the determinant is A times D minus B times C. Let's prove this with an example. If we take matrix A with 2, comma 3 in the first row and 1, comma 4 in the second row, the determinant is 2 times 4 minus 3 times 1, which is 8 minus 3, giving us 5. Since this isn't 0, matrix A can be inverted, and here is its inverse. If we take matrix C with 2, comma 4 in the first row and 1, comma 2 in the second row, the determinant is 2 times 2 minus 4 times 1, which is 4 minus 4, giving us 0. If we look closely, row 2 is exactly half of row 1. The rows are linearly dependent. Whenever the determinant is 0, the rows or columns of the matrix are linearly dependent, and the matrix has no inverse. Here is why that actually breaks things. Remember from the matrix inverse video, a matrix represents a system of equations Ax equals b. If we write out what C actually says, it's 2x plus 4y equals b1 and x plus 2y equals b2. The second equation is just half of the first. It doesn't give you any new information. You effectively have one equation trying to solve for two unknowns. That means one of two things happens. Either b2 happens to equal half of b1 and now infinitely many pairs satisfy both equations, or b2 doesn't match and no solution exists at all. Either way, there is no single unique x that maps back to a given b, and an inverse only exists if every b has exactly one x. That's the actual reason a zero determinant means no inverse. Linear dependence means you don't have enough independent information to pin down a unique answer. This extends to bigger matrices too. If we consider a 3 by 3 matrix M, the determinant is A times EI minus FH minus B times DI minus FG plus C times DH minus EG. Let's try it with an example. That gives us 2 times 3 into 1 minus 2 into 1 minus 0 plus 1 times 1 into 1 minus 3 into 0, which is 2 times 1 plus 1 times 1 giving us 3, a non-zero. So this matrix can be inverted. You can see this gets tedious fast as matrices get bigger, which is exactly why we don't do this by hand in practice. Here is how to do it in numpy. We define our matrix as a numpy array and use numpy's linear algebra determinant method to calculate it directly for a matrix of any size. So why do we care? In machine learning, you will run into the determinant when checking whether a covariance matrix is valid, when working out if a system of equations has a unique solution before you try to invert anything, and in the change of variables formula used in probability distributions. If you haven't seen it yet, you can watch the matrix inverse video here to understand how to calculate the inverse of a matrix. I'll see you in the next one.